Hello again. Welcome to week 2, where we're going to be talking about forecasting and how artificial intelligence is being leveraged into this space. Similar to last week, nobody signed up to present this week, so I'm going to cover that for you so that you can earn your participation credit for the week. Please go ahead and create a new thread with your comments after this presentation, and then you have until next Tuesday to respond to other people's threads. I think things went pretty well last week in that regard, so keep that up going forward. Okay, so let's talk about forecasting and artificial intelligence. So real quick, let's just start with an overview of AI in general. When AI was first coined, the phrase in the early 1950s, computers had only been around for about a decade. And artificial intelligence was the thought of using computers and systems and software to emulate human problem solving, reasoning, induction type thought processes. Some of the first uses of AI were called expert systems. And expert systems is where they tried to codify how an expert would approach a problem and the steps they would take to solve the problem. And they tried to translate that to if, then, and or statements in software to work through a series of steps to come to some sort of conclusion or outcome based on how an expert would have approached that process. These can be broadly separated into crisp and fuzzy logic type systems. A crisp system is like your air conditioning unit at home. You set the thermostat at, say, 75, and once the temperature hits 75 degrees, the air conditioner comes on to cool the house down. A fuzzy system is similar, except instead of having very crisp rules, such as at 75 degrees, turn the fan on, it's built around a series of fuzzy rules, such as when it is getting hot outside and the humidity is high, then start to turn on the air conditioning system. So instead of very crisp decision points, they're much more fuzzy. This became part of the ecosystem of artificial intelligence to also include things such as vision recognition, language processing, generative video, generative picture making, all of these other aspects. And one of the big ones that specifically deals with demand forecasting would be machine learning subset of AI. So it can be broadly split into supervised and unsupervised algorithms, meaning that supervised is where an operator has direct control over the implementation of the algorithm, the data that it uses, when and how it runs, versus an unsupervised model. A lot of that is left to be determined by the model itself. Basic regression models are very common in these supervised type machine learning models, and that's basically how a lot of forecasting has been done in the past. We can move on to some different architectures, what are called neural networks, and these are nodes and linkages built in layers of data information exchange, where it's meant to emulate the human mind and how humans process data. And these neural networks can be very complex interactions between different variables and their associations. And then the subset of deep learning combines neural networks and unsupervised learning, where information can move backwards and back propagate through the network in a much more autonomous level of AI. So I'm not too concerned about all of these differences. Just wanted to give you a high level overview of different types of AI and how they're related with each other. Traditional forecasting can be split into two big branches. The first is qualitative, which is essentially opinion-based forecasting. And this is appropriate when you're launching a product that's new to the world, never been done before. You don't have data on actual sales or demand, or maybe you're launching a product in a new market such that you don't have data on how it's going to do. For example, when Apple released the iPhone 15 in China, that was the first time that an iPhone had been released in China. They didn't really understand what demand would be there. They were able to estimate based on other cell phones and demand in the United States, but they still missed the mark by about 2 million units, which isn't terrible, but it's 2 million opportunities for lost sales. Next is quantitative. So this is data-based forecasting. And the most common that we use is time series, meaning I've got historical records of past sales that I'm going to use to generate a forecast for future sales. And with this, we can account for a lot of daily or seasonal trends and in the data, such that if we know that first quarter sales are typically soft, I would expect the next first quarter to also be a little bit soft. One of the things that we can tune in these models that we'll see in a minute, especially in the exponential smoothing, is the amount of stability versus responsiveness. So for example, if we see that demand this week for a particular item was unexpectedly high, how should we treat that data point? If we tend to believe that that's more of an outlier and just not to be repeated, then we would want to tend to have a more stable forecast to discount that as an outlier. Alternatively, if we wanted to think that, oh, that's maybe a change in upward trend, a new pattern that's going to exist, then we need to have a very responsive forecast to account for that as the new reality. So that's a trade-off that we have to make on how do we treat these data points that vary significantly from what our forecast was expected to be. So most modern algorithms today that deal with forecasting are based on exponential smoothing models and regression models. So exponential smoothing models essentially incorporate a smoothing coefficient to balance this stability responsiveness trade-off. We have single exponential smoothing models where we expect demand to be relatively constant and only change mildly throughout the time frame. We have double exponential smoothing, which can additionally account for positive and negative trends in the data. And then we have triple exponential smoothing, which can then incorporate seasonality into the data. These are sometimes called a Holt-Winters model. And then we have regression-based models, where we have dependent variable, which is typically unit demand or unit sales for any particular item in our portfolio, related to a variety of things: past demand, price, time of year, what competitors are doing, so on and so forth. So we can build very elaborate regression models with known relationships between the variables. And then we can adjust these models to see if we add or subtract various components, if we get better, more accurate forecasts going forward. Like I mentioned, most ERP systems today combine aspects of these two forecasting techniques to generate forecasts going forward. A problem that we often exhibit, and is much more pronounced in AI, is what's called overfitting the data. And it's essentially where, instead of understanding the general relationships between variables and the outcome, in this case demand, we can develop a model that exactly maps at a one-to-one positioning of an input to an output. And the problem with overfitting is that it doesn't yield reliable forecasts. So here's a quick example. Suppose I want to estimate my sales as a function of marketing. And if I've got two data points, I might want to set this up in a linear regression that looks something like this. So the more I spend in marketing, the more sales I should receive. This is, a pretty reasonable trend I would expect to see. Now, suppose that I built this same model, but I used 4 data points. So it's still a simple regression model based on marketing. And as you can see now, I no longer perfectly fit the data. Okay, so this is a good estimate of an upward relationship between how much I spend in marketing and how much my sales would be. Now, an example of a completely overfit model would say, maybe I can make this forecast even better. Suppose I include, not only marketing, but marketing squared and marketing cubed into my regression equation, such that I can now actually perfectly map the data. And so you can do this with any model. You include enough variables into your prediction model, and you can perfectly map the data. The problem is this is not going to yield an accurate forecast, especially if you extrapolate. So if you move beyond the bounds of the data at which my model was built, in this case, marketing spend of less than 1 or more than 3, my results are no longer reliable. As you can see from this model, if I don't spend anything on marketing, I'll have the highest sales. So why spend marketing at all? Similarly, if I spend more than 3.75 in marketing, well, then I'm going to have negative sales. People are going to return all the products that they've ever purchased because they're sick of seeing my commercials. So neither one of these make much sense. And it's because we're extrapolating beyond the bounds that our model was built. In addition to this time series data, AI models can incorporate vast amounts of data, and you don't have to specify the functional relationship between the data points. They can incorporate competitor information, financial information from exchanges, maybe information on supporting products and services for your products, such that, ancillary services and products that people would purchase to use with your products, right? The challenge that we have with a lot of AI forecasting models is they result in what's called black boxes, meaning that we don't necessarily get to see the equations that are used to generate the forecast. And so because of that, it's difficult to determine if there's any theoretical flaws in the forecasting model. Other challenges that we have are that, AI models make mistakes, and they have what's called AI hallucinations. They can also be biased. And so we're going to see examples of all of these in a minute. But first, how does AI actually, work at the high level? Well, essentially, you start with some set of data and you split it into two, a training set and a testing set. And you get a training set with a portion of your data, and you include all of your input and output variables, and you essentially let AI or structure AI to build models trying to predict these outcomes based on all of these inputs. And these can be highly nonlinear, highly complex models. And then you test the model that appears to best on the training set against this testing set, the holdout data that it's never seen before. And you see how well your model predicts the outcome. Perhaps you have to go back and use different models to get a better testing set prediction algorithm. And then once you've done that, you can then launch an actual AI model. Now, in real world applications for a while, these will be launched in the background to gauge how well they actually perform instead of replacing an existing system, just so you're not going to jeopardize current operations. But then once it's launched for real, there are two high levels of how these are managed going forward. You have static models, which use the training data model that was built, and it applies those parameters to future information to build forecasts. This can be good in that it provides some stability, and you always know that your forecast is treating data the same way. But the problem is it doesn't account for changes in the market, changes in the competitive landscape. So you can also have dynamic models, which incorporate new information as it comes in to build better, more reliable forecasts going forward. Okay, so I mentioned hallucinations before. Hallucinations from AI is when an AI output can be not just totally wrong, but often completely made up. So it's not referencing some inappropriate data point. It's actually creating something out of potentially nothing. You can do some searches. It's kind of humorous. There's been multiple lawsuits now where lawyers were trying to do a background check on previous case law to support their argument. And so they asked AI to provide a list of similar court cases and outcomes. And turns out on more than one occasion, I know of at least three, where AI really created entire legal structure out of thin air, in which lawyers did not know this. They did not go back and double check the reference and included this into their legal briefs, at which point they were later caught by the judge saying that these cases aren't real, you're citing fictitious things. Similar things have happened on live streams, ironically, when trying to tout the benefits of new AI systems, where they would ask some AI to analyze financial statements of companies. And then in that analysis process, turns out the AI would sometimes just completely fabricate financial data to support some argument that it was going for. Similar to the first case, there's been lots of cases where researchers wanted to understand some background work on a particular topic, maybe carbon dating or nuclear fusion or whatever, it doesn't matter. And they ask AI to give it some prior references to look at, and it will generate not only a fictitious citation, but fictitious works associated with that citation. So these are all examples of what we dubbed as AI hallucinations, where AI is creating data from nothing. And why does this happen? It could be models being overfit. So similar to my extrapolation in the marketing model I showed earlier, it could be it did not have adequate training data. It could be it's being asked to do something at which point it's completely outside of its realm of base knowledge. So there's all sorts of reasons, but you have to be aware that this does happen. Next is AI mistakes. So it's estimated that between upwards of 20% of all AI generated responses to chat GPT type questions potentially have partially or totally incorrect information in them, which is a huge number. And it's related to this AI hallucination and mistakes. So a classic example of a mistake is AI doesn't understand slang. So an NBA player did a social media post about shooting bricks, which means he was hitting the rim pretty hard, wasn't making shots. Well, AI then created an entire story about how this player went on a rampage and started shooting houses in a neighborhood. But the article did report that there were no injuries reported. Well, it's because it never happened. It took the shooting bricks to mean that this player was actually shooting a gun at people's homes. AI doesn't understand satire. There's a popular website called The Onion, which is a satirical news site. Google actually referenced an article that The Onion had made up where a fictitious geologist claimed that humans needed to incorporate more minerals into their diet, and so they should eat stones daily. Well, Google then cited this fictitious geologist as claiming that people should start eating stones, again, not realizing that it was satire. And then we have the fake news problem. AI is more and more being used to generate fake audio, fake video, fake pictures of events that did not happen. Well, then other AI is tagging these as proof that these things existed. And so we've got this huge misinformation cycle that is spreading by the creation of fake news and then the propagation of fake news through AI searches. Last is AI doesn't understand often the difference between opinion and fact, such that things taken from blogs or editorials or opinion pieces, it might attribute those as being factual-based statements instead of somebody's interpretation or somebody's opinion on a topic. And then we have AI bias, right? So just like humans, unfortunately, AI can result in biased outcomes. And this typically happens when it is trained and tested on data that was biased to begin with. So a classic example was early financial institutions, early uses of AI in financial institutions were training AI based on prior credit ratings that they had assigned to their customers based on a long list of financial credentials. Turns out that the AI model was then yielding biased results against minorities, giving them higher interest rates. And it was simply a function of the fact that the humans who had coded the data originally had given minorities higher interest rates. And so that was propagated through to the AI. Similarly, in HR uses to screen resumes, data was trained on a stack of resumes that were granted an interview versus ones that were not granted an interview. And turns out that when the AI algorithm was analyzed, it was disproportionately rejecting women and elderly people simply because that's what the humans had done on the training data. So it had just maintained its way through. It can also happen if the training data does not represent the entire population of data that's going to be used. For example, early facial recognition software had a real hard time understanding and doing facial recognition for people with darker complexion. So it was built and trained on people with lighter complexion skin, and people with darker complexion, it did not do very well. There's also the problem of static temporal bias. So consider an AI algorithm based on forecasting based on data from the year 2019. If that model were applied to the year 2020, you would have totally incorrect answers because it had not been updated to more recent information, such as the pandemic. Now, what makes AI forecasting unique and special? Well, in traditional forecasting, like I said, it's reliant on somebody building a model with known relationships between the variables, right? AI models can incorporate a vast array of data, and it may only use a subset of that. It may include interactions that are not planned, and it can include linear and non-linear relationships. So it's able to do a lot more with the data than we would think about doing ahead of time. As a result, these models can become much more accurate than traditional models. They can be dynamically adjusted in real time as new data is introduced to the system. And AI can clean and organize data that's somewhat messy. If anybody's ever dealt with large data, Oftentimes it's not labeled correctly. It's got holes in the data where it's missing values. Sometimes it's coded incorrectly. So AI has the ability to clean all that up and make use of data that would take a long time for humans to be able to do. But at the end of the day, it's still going to be a black box methodology. So we have to keep humans plugged into the system. If it's done well, here's some of the benefits, right? Their forecasting accuracy, this data all comes from McKinsey cited at the bottom. More accurate forecasts, approximately 10% more accurate, meaning that they can have fewer errors in their inventory management system as far as specific line item errors. They can reduce stockouts by up to 65% and reduce excess inventory by 10 to 15%. So these are what you look for in better forecasting, is better inventory management so that you can supply demand. You can update these quicker, such that as market conditions change, AI has the ability to adapt the forecasting algorithm to new market conditions. It's estimated that you can generate forecast in half the amount of labor required to do so. So these are great savings from a business perspective on how we can leverage AI to get better firm operations. All right. Look forward to you guys' comments. Have a wonderful week, and let me know if you have any questions. Take care.